In this video, we're going to introduce you to direct, inverse, and joint variation. We skipped a section early in the year that talked about direct variation, and all direct variation is a simple equation that says y equals some constant k times x. This is just a linear function, and k, that coefficient of x, this is called the constant of variation. And it's called the constant of variation because it is the one thing that remains constant in the equation. And the only thing that changes from one direct variation problem to the next is that k value. So an example that I gave you is y equals a half x. Here, in that example, k, of course, is just a half. So k can be any real number except for 0 because that wouldn't really be direct variation anymore. That'd just be a straight horizontal line. On the other hand, inverse variation has the equation y equals k over x. So now we have x in the denominator of the fraction. So here, k is still called the constant of variation. So an example that I gave you here is y equals 2 over x, where just 2 is your k value in that particular instance. Let's go on to the next slide. Here I'm going to ask that you classify whether an equation is direct or inverse variation. So it could also be neither in this particular example. So we're going to do a few of them together. I'm going to leave you a couple to try maybe on your own at the end. For A, we have x over 5 equals 3y. It's kind of hard to tell what type of variation that is based on that particular setup. It's going to help if we rewrite the equation where we have the equation solved for y. So since y is being multiplied by 3, I could divide both sides by 3, but since I have a fraction over here, I don't want to have a fraction and a fraction. So I'm going to multiply by the reciprocal of 3, 1/3. If I multiply both sides by 1/3, the 3's over here are going to cancel, and I'll end up with y equals, and I'm going to go ahead and write that on the left side of the equation. On this side, I'd have 1 times an x in the numerator, so just x in the top, and in the denominator, I'd have to get 3 times 5, which is 15. So the equation really is y equals x over 15. Now here, you might be thinking, oh, that's inverse variation because I see a fraction. However, notice how x is in the numerator. Another way of rewriting the same exact equation would be y equals 1/15 times x, right? That's the same exact thing. If we multiplied 1 times x and 15 to the 1, we'd end up with x over 15. So really what we have here is direct variation. This is direct, where the k value is 1/15. That's what we're multiplying x by. So that's kind of a tricky one. Let's take a look at part B. Here, if I was going to solve for y, multiply both sides by 5, and the 5's can cancel, and I'd get y equals x times 5, or just 5x. That's pretty straightforward. That looks like y equals kx, right? Y equals kx being direct variation. The k value here is 5. So if I write k equals 5, we know that this is our direct variation. For part C, here I have y over x equals 4. If I was going to solve for y, I can just multiply both sides by x, and the x's cancel, and I get y equals 4x. Oops, let's rewrite that. Get y equals 4x. Once again, this does fit that same pattern, k value being 4. This is direct variation. We might as well just do the rest of them, D and E, together, because we're going to kind of understand a pattern here. If I solve for y in this case, what I could do is multiply both sides by y to bring y up in the numerator. The y's will cancel over here, and if I rewrite what we have, we just have x equal 4 times y. Now what I'd have to do is divide both sides by 4, and I'd end up with y equals x over 4. Once again, this is not inverse variation. X is in the numerator. Another way of rewriting this would be y equals 1/4 times x. K value here, our K value, if I can make a better looking K, that's even worse. Our K value here is 1/4, and we're still playing with direct variation. This last one, I have x times y equals 5. If I get y by itself here, I'd have to divide by x, and I'd end up with y equals 5 divided by x. Now here is the only time where x showed up in the denominator. So this kind of fits the pattern y equals the constant divided by 5. That's inverse variation with a k value of 5. So this is inverse variation. Now, it wasn't super obvious, but if you took a look, if we were dividing y by x and we got a constant here, and I think we did if I erase some of my marks over here. Let's see if there was any instances where we saw y divided by x. And here there's one right here, and in part C, you'll notice when we divided y by x and we ended up solving, we ended up just getting direct variation, and the k value was that 4 that the quotient y over x was equal to. So this ends up being just direct, this ends up being direct variation. Because actually, if we took a closer look at this, if we have y over x equal to some constant k, if I solve that for y, I'd have to multiply both sides by x, right? To cancel out the x in the denominator there, and I'd end up with y equals k times x. And that is the formula for direct variation. It's just another way of writing it. The last example, when we got x times y equals 5, ended up being inverse variation with the constant of variation being 5. So if you have the product of x and y is always constant, that's going to be inverse variation. If you took this formula, x times y equals k, and you end up solving for y by dividing by x, you're going to end up with the inverse variation formula, y equals k over x. We have our inverse variation. Now, what we're going to do next is we're going to actually look at some tables and figure out if we have direct, inverse, or no variation between x and y. If it's direct or inverse variation, we're going to write an equation that models the data. So take a look at A with me. Here we have A and B instead of x and y. Just to make this maybe a little bit simpler, let's think of this as being x and the B value as being our y, the output. So just go ahead and change that. Now, there's a couple ways we could try to do this. To me, the easiest way to try to figure out if this is direct or inverse variation, or even neither, is to see what happens when we do y divided by x. If we take the quotient of the y value over the x value, do we always get the same constant? If so, remember this is direct variation. If, however, that doesn't work, we can try multiplying the x and the y values and seeing if that's constant. If that's true, this is going to be inverse variation. So let's see what happens if we try the first option. If I do y over x, if I set up my y over x, actually maybe let's do that in the following manner. Let's make another, I'm going to erase a little bit of what I have here. I'm going to make another piece of table here, and let's kind of figure out what y over x is in this row. So in this case, if we do y over x, we'd have 21 over 5, which is 4 1/5. If we do it over here and do y over x, that'd be 10.5 over 10, and that is not even close to 4 1/5. That's like what, 1 1/20th, I think. So this is not going to work because these aren't going to be equal to the same values. Let's try, on the other hand, what if we did x times y? Let's make another column here and check what happens if we do x times y in each case. In the first couple of data values we have for 21 and 5, if we multiplied 21 times 5, I think we're going to get 105. All right. What if we multiplied the x and y value in the next spot here? If we do 10 times 10.5, that's going to be equal to 105. And notice, so far, we have the same output, the same x times y value, that same constant. It's not good enough just to check these two values. We want to make sure that we get 105 all the way across. If we don't get 105 all the way across, it's not going to be that inverse variation. So let's try this next one. If we did 15 times 7, 10 and 7 is 70 plus another 5 times 7 or 35. That's going to give us another 105. So far this is looking pretty good. Let's check out 20 times 5 and a quarter. If you multiply those, I do believe you are going to get 105. And the last example, 25 times 4.2, if we multiply those, you also get 105. So in every case, when we multiplied x and y, we got 105. That should tell you that x times y in this example is always equal to 105. And guess what? That 105 is your k value. All right, so I think if in the problem it told us we have to identify whether it's direct or inverse, and if it is, write the equation that models the data. So I know right now for part A, it is inverse variation. And remember, inverse variation, the usual way we write it is y equals k over x, and we know the k value is 105, so it's going to be y equals 105 over x. So if I wanted to get another value for y, I can plug in whatever x value I'd please, and just divide 105 by that number, and I'd have a new y value. Guys, in general, when we have inverse variation, check out what's going on. As the x values get larger, right? As we plug in bigger and bigger x values, you'll notice what's going on with these y coordinates here. 21, 10 and a half, 7, 5 and a quarter. Every time we jumped by 5 for x, these y values got smaller and smaller. That's inverse variation. As one variable gets larger, the other gets smaller. That's just generally speaking what happens with inverse variation. Let's look at B together. I'm going to do this in the same fashion, although I'm just going to build onto the table in this way. Let's go ahead and see if we have better luck with trying y over x here. So if I do y over x in this example, I'd have 12 over 3. 12 divided by 3 is 4. Okay, let's try the next row. If I did 32, the y value divided by the x value of 8, I also get 4. Now again, I'm not going to get too excited and just assume the rest of the values are going to give me a quotient that's 4. I need to double check them. So I'm going to go ahead and divide 44 by 11. And once again, I got 4. I'm feeling pretty good about this. If we did 2 divided by 0.5, that's not a decimal actually. That's 2 divided by a half. That is going to give you 4. So in this case, we have something that fits the form y over x equals 4. In this case, 4 is our constant of variation, but this is not inverse variation. This is direct variation. So when the quotient of the y and x gives you the same constant, that's really going to be of the form y equals k times x. But we know our k value is 4, so I can write y equals 4 times x. So basically what this formula means is, give me an x value, right? I'll plug it in and I can get my y value just by multiplying it by 4. And if you take a look, that does make sense. Look at these x values. 3 times 4 is 12. 8 times 4 is 32. 11 times 4 is 44. And 4 times a half is 2. Notice also in direct variation, as the x value increases, right, 3, 8, 11, although a half kind of jumps down to a lower value, but at least for the first three, as these increase, the y values also increase. So generally speaking, in direct variation, as one variable increases, the other does as well. Or if one is decreasing, the other decreases. They're going in the same direction. One gets larger, the other gets larger. If one's getting smaller, the other will also get smaller. Unlike inverse variation, we go the opposite directions. I think you guys should be able to try C and D. Hopefully you have an idea of what's going on here. Just be careful. Make sure when you check the quotient or the product of x and y, you check it all the way through. There might be one pair of values, x and y, that mess you up. Now, here what we're going to take a look at is how we can write an equation that models the information and then also use that to find a new y value when x is 4. So the key statement here is that the variables x and y vary inversely. If it doesn't tell me that, I'm going to have no idea what to start with. Now, if x and y vary inversely, there's two things that might come up to mind. The first one might be y equals k over x. That's the general inverse variation model. Now, in these problems, guys, when you write the model, you need to figure out what k is. Another way of writing inverse variation that makes it easy to find k, if you recall, is just x times y equals k. These are equivalent, remember, they're just written in different ways. So for part 1 here, if I have to find the equation that models inverse variation using the x value 3 and y value 2, I'd rather use this formula to find my k than this one. So if I just substitute in 3 for x and 2 for y, I can figure out my k value is 6 very quickly and easily. And then I can use that 6 to write my inverse variation. I can write y equals 6 over x. I would go back to this formula and just plug in the 6 that I know is the constant of variation. So there's the equation that models my data. What I'm going to do now, that's technically part A, right? I just found so for part A, there's my answer. That's the equation that models inverse variation when x is 3 and y is 2. For part B, what I'm going to do is I'm going to find the value of y when x is 4. So for part B, we want to know what y is if x is 4. Well, this is going to be pretty easy once you have the formula for part A established. I can just write y equals 6 over 4, which reduces to 3 over 2, or 1.5 if you'd rather write it like that. So there's my answer for part B. I'm going to ask that you guys try this one on your own. It's the same problem, but just different numbers. You're trying to find the equation for A that models the inverse variation, and then for part B, you're going to find what is y when x is 4. Okay, so go ahead and give that a shot. The last thing that I'm going to show you guys in this video is joint variation. Joint variation is just when one variable varies directly with two or more other variables. Then we would say that the variable varies jointly with those other variables. For instance, if y varies jointly with x, z, and p, then we would just simply write y equals, we still have to use a constant of variation k, and then I'm going to write x, z, p. So y is equal to the product of k times x times z times p. What I'm going to ask that you guys do is write the joint variation equation for each of the following models. And I'll maybe do the first couple with you and see if I can challenge you to do maybe the last one or two on your own. V varies directly with u. Okay, well, there's only two variables here, and since it's direct, I can write v equals k times u. That's direct variation. For the next one, p varies inversely with j. I'm going to write p equals, and since it's inversely, I got to make sure j is in the denominator of the fraction. I'm going to do k over j. Now c is where it starts to get a little bit more interesting. It says w varies jointly with t, u, and b. So w is what I start with, and I always say it's equal to k. So now it's varying jointly with t, u, and b. So I'm just going to copy down the product of t, times u times b. So w equals k tub in this example. Maybe we'll do one more with you, and then I'm going to give you kind of the granddaddy to try on your own. For d, v varies inversely with the cube of g. So varies inversely. So I'm going to write v equals, now since this varies inversely, I'm going to write k in the numerator. In the denominator, I have to write the cube of g. Notice it doesn't say the cube root of g, it's just the cube of g. That's a fancy way of saying g to the third power. So I'm going to make sure I put g to the third in the denominator there. For part E, it says f varies directly with the cube root of h and inversely with the square of d. I'm going to have you guys try that one on your own. That's kind of a fun challenge one to try and see how you do on your own. One last example. I'm sorry, this one's kind of a long one. The variable z varies jointly with x and y. Right there, if you know z varies jointly with x and y, hopefully you can write something like this. Z equals k, then x and y. Doesn't say inversely anywhere, so no variables go in the denominator. It says use the given values to write an equation that relates x, y, and z. Then find what z is when x is 2 and y is negative 1. First, to write my equation, I have to use these three variables, or the three values, and substitute them to find my k value. So I'm going to put in for z a 3. I don't know what k is, that's what I'm actually trying to find. For x, it tells me x is 1, and the y value's got to be a half. So I can solve this. I can get 3 equals, and if I multiply 1 times a half, that's just a half, right? So 3 equals a half times k. If I were solving for k, I'd multiply both sides by 2, cancel with the half, and I get my k value is 6. So my constant of variation is 6. So the model for this equation is z equals, and instead of kxy, I can write 6xy. So that's the first part. There's my model, or the equation that relates x, y, and z. Now for the second part, it says find z when x is 2 and y is negative 1. So they really want to know, what is z if x is 2 and y is negative 1? So let's plug that into our formula. So z equals 6 times 2 times the y value, negative 1. I'm going to get z is, what is that, negative 12. And then we're done. Guys, I'm going to have you try b on your own. Again, it's z varies jointly with k, or with x and y, so you should start with that same formula. Figure out the k value, write your equation, and then substitute in the new values to find your z value. Good luck with it, guys, and we'll see you tomorrow in class.